for homework on Monday. There's plenty of paper up here. Feel free to take paper. Okay. Four questions, four pieces of paper, right? One question per page. Make sure your name is on the first page and everything is stapled together. And then make sure the question, problem number, and section number question number is on every page. Well, plenty of paper here. Help yourself. I figure I'm demanding to use that much paper, so I should supply it to you, right? So you can't say to me, well, I don't want to use all that paper. Well, I'm giving you the paper, so use the paper. It's just easier for me to grade when it's that way, okay? I have our schedule up here. So everyone has the questions. They're posted on Blackboard, right? I'm going to do that from now on because I know it's tough for some of you to, if you're not here when I write it down, how do you know it, right? If you don't watch the video when you're not here, you wouldn't see it either, right? So I'll be putting, I think we should only have 2 more homeworks left. I usually don't give homework in chapter 5, so it might be only 1 homework. Chapter 5, I just figured now you know what to do, so I don't have to bother with it anymore. If you have questions for me to do, please send them to me. It looks like our chapter 4 test will be on November 11th. That way you have a few days. You'll get your test back on the 14th, and then you have to the 15th to decide to drop the class or not, right? Our chapter 5 test is on December 2nd. Then we have 3 classes of review for the final, and then the final, right? I forget which day our final is on, Monday or Wednesday, but it's in the syllabus, and I'll remind you when we get closer, okay? Any problems for me to do today? If not, it's great. We'll just move on. We're doing optimization today, 4.6. It's not difficult. It's just very long and lots of writing, just like everything else so far. Chapter 4 is all like that. Okay. So just be patient. Make sure you have the step-by-step on your formula sheets, because that's what you'll forget. Not the, the calculus we're doing is finding derivatives. So that's not difficult for you, right? But what's difficult is remembering what to do and how to write it up. So you just make sure you have that on your formula sheets. So no questions? I can go ahead. Let's see who's here. Chris is not here yet. Jack's here. Daniel, Jeffrey, Matthew, Anissa, Mr. Ariana, Abigail. Abigail's not here. Roger's here. Molly's here. Chrissy's here. Yes. Candace is here. Petra, Boy, Chadri. Nice. Everybody but Chris and Abigail are here. Awesome. All right, here we go. We're ready. New stuff, yes? So we're talking about 4.6 today, optimization. Like, for example, I'm making boxes out of cardboard, right? And maybe I'm cutting out the pattern from large sheets of cardboard. I'd like to minimize the waste, right? Maybe I have some function that tells me how much profit I'm making depending on the number of products I'm making. Maybe I'm making bicycles. And if I make too little, I don't sell enough. right? If I make too much, maybe I have too much on stock and I'm losing money that way. So maybe there's an optimal place for me to the number of bicycles I can make that will maximize my profits. And that's what we're talking about. So optimization problems. And we want to find a min or max. Using a first derivative, and verify min or max using the second derivative. So we'll do a quick example. The types of problems that I like, so problem types, are either geometry, like a box, right? Maximize the volume of a box given this much cardboard, right? That kind of thing. Or distance problems. And so I'll probably put a geometry one on your quiz, and I'll put a distance problem on your test. That's what I usually do anyway. The problems I'd like you to do right now are 1 to 47. But keep them to those types of problems. You'll see it'll say find the min distance or find the maximum area or etc. like that. So geometry and distance problems, okay? Better yet, geometry meaning some volume or area of some shape, right? And then the distance problems is usually always find the min distance, okay? All right, let me do one particular problem, and then we'll do our step-by-step, and then we'll do a more difficult problem, and then we'll talk about the distance problems. So our first problem is, I think this is 4.6, number 2. Find real numbers, x and y, such that x minus y is 100 and x times y is a minimum. So this one's not really a geometry problem. I will say first, when we do our step-by-step, try and draw me a picture, right? Even if it's a min-distance problem, you should be able to draw the graph or the function and the point where they want you to minimize the distance. But for this one, we're just going to go through the process knowing that we need an equation and an expression. So every time you're doing one of these problems, you'll need to find an equation and find an expression. Usually it's given to you, but sometimes you'll have to get it from the geometry, right? So like if you drew a rectangle, right, with base x and height y, you know the perimeter, right? You know the area, right? So 2x plus 2y is perimeter, area is xy. But that's just, again, I'll put that into the step-by-step. You need an equation and you need an expression to maximize or minimize. Of course, the problem here with our expression is it's 2 variables. So we're not ready for that. The engineers in here will take Calc 3, and that's when you start to have 2 variables in your function or 3 variables in your function or n variables, multivariable calculus, right? Who are my engineers here? Nice. So that's a great class. That's the perfect class to take in summer, Calc 3, because it's so easy. Okay, so think about that. Have you all put your schedule together yet? With you can go on Blackboard and create your schedule for the whole semester. Have you seen that? It's in academic plan. So you go into your academic plan and you can start to schedule all your classes where they will be, and you'll see when you're finished, right? That's a pretty cool thing to do. Maybe over Thanksgiving break, maybe. Okay, back to our problem. So what I'm going to do is I'm going to take my equation and sub it into my expression to create a function in x, right? So x minus y equals 100 gives me what? Y equals x minus 100. Yes, you agree? And then I'm going to take that, right, into x times y, which now will become x times x minus 100. And there's my function I want to minimize. So you're going to have an equation. You'll solve for a variable, plug it into the other expression to create a function in one variable, and that's what you're going to do your first derivative test with, your second derivative test, right? Everybody with me? So let's get our critical here. F prime of x is what? 2x minus 100? So f prime of x equals 0 when x is 50, yes? So that's my min value, at least I think, right? That's where my minimum is going to occur. Of course, I should double check with the second derivative. F double prime of x is just 2. So f double prime of 50 is still just 2, which is positive. Positive people smile, so I must be at a minimum, right? And then, of course, I want to just answer the question, right? What is the question? What are the two numbers? What's your minimum value, right? So if x equals 50, x minus y equals 100 gives me y is negative 50. So with 50 minus a negative 50 equal 100, x times y is minimized at what? 50 times a negative 50, which is negative 2,500. So once I get everything verified, I find my minimum, I verify it's a minimum, I find all my values, I write up a solution to the problem. So answering everything in the problem, right? Yes, we okay? It's pretty easy. It really is easy. Probably the hardest thing is coming up with the equation and the expression. But then after that, it's just derivatives, right? So not difficult at all. All right, let's look at a problem from the book. We okay here? Oh, wait, yes, mister. Say that one more time. Yeah. So I find my first derivative. I find that critical value. It's obvious. In this case, it's obvious. I have a quadratic, right? So I'm finding that low point of that quadratic, right? So I found that. I've solved for my second derivative and then plugged in. And now remember, when the second derivative is positive, we're talking about someone smiling. It's obviously right from the original function. So it's got to be at a low point there. It's got to be minimized. Positive people smile, so it must be at the bottom of the valley. Yeah, Matthew. It's right. So when the second derivative is negative people frown. I'm got to be at the top of that hill. Maximize. Yeah. And of course you can always move to Desmos Once I get my function in one variable, I can do everything like I've been doing on Desmos with the first derivative test, right? So probably at this point we're a little bit more confident knowing that that I don't need to look at the function, but of course you can, right? At the graph, of course you can. Yes. Good. Okay, no problem. So looking at our book here, maybe not. Oh, here it is. So like number 13 is a good geometry one. Number 8 is a good min distance one, right? 13, you were constructing a box. Number 8, we're finding the distance from a point to a line. So et cetera, right? Odd problems. Well, you could even do even problems because you'll know if they're right or wrong. I'm having a hard time with my view here. Let me just open the book again, sorry. I think priority registration for next semester starts next Monday. I could be wrong about that, meaning, so if you have 30 credits finished, you can register early, right? That could be some of you. If not, you just wait one more week, all right? Once it opens up completely, I'll tell you. If you're early college, you don't care. They're scheduling everything for you, okay? Oh my God, why is it so slow? Oh, let me do my step-by-step, sorry. Let's do the step-by-step. Read the problem. A lot of times, the information is right in there. Like the problem I just gave you, the equation was in there, the expression was in there, right? Draw a picture. They might ask you to, like the one we're going to do is going to be a square base with an open top. So square base, right, x by x, and an open top. So that's the problem a lot. So I've got a box. I want to maximize my volume and minimize my surface area, right? So I don't know how high the box is, right? But we'll call it y kind of thing. So read the problem, draw a picture, right? Find or create an equation in two variables and an expression to be minimized or maximized. That's also in two variables, right? You're going to have some kind of x, y every time. Read the problem. Draw a picture. Find or create an equation in two variables, an expression in two variables, and right, we're going to try and maximize that expression. Solve for y in the equation and sub into the expression to create a function of x. How we doing? You with me here? We're going to do an F prime test to find the critical. An F double prime test to verify the min or max. And then answer the question. Okay, let's do a problem. How we doing? We okay? You got it? All down? Almost? Okay, I can wait. My father used to say, you'll never be a doctor if you don't have patience. So again, another horrible step-by-step long list of things to do. And certainly that's probably all you need on your formula sheet is how to do it. Maybe another problem worked out is a good idea too. At least one geometry problem, at least one min distance problem worked out on your formula sheet. You should be running out of room. Hopefully you can start taking things off of that formula sheet. You certainly can write smaller, right? All right, let's do a problem here. Let me open the book. So chapter 4, optimization. Let's do 15. I don't know. Can you see it? Probably not, right? Trying to zoom in on it. A farmer wants to fence in an area of 1.5 million feet squared. And in a rectangular field, right? Then divide it in half with a fence parallel to one of the sides of the rectangle. We want to minimize the cost of the fence, so we want to have a minimum perimeter, and obviously we know the area, right? So this is 4.6, number 15. What is it, 15? Yeah, 15. So right here's the field the farmer has, right? It's a rectangular area, and the area is so the area equals 1.5 million feet squared. So obviously, I can pick. And he's dividing it in half, right? Dividing it in half. So I'm going to call the height here y, and each of these bases x, right? Each piece here is x. That makes sense? So what is my area? What's the actual calculation of my area? Right, 2xy? And I know it's 1.5 million. I know it's feet. The units are feet. I don't need to worry about that too much. We'll let your science teachers worry about the units. I need to find the critical number, right? I know it's going to be some x value in feet, right? We're trying to minimize all of this fencing, right? This is fencing. So how much of the fencing do I need here? What's my perimeter? How about that? How many y's and how many x's? 3 y's and 4 x's, yes? We want to minimize that value. Minimize that value. So here's my equation. Here's my expression that I want minimized. Right? Step 1, read the problem. Step 2, draw the picture. Right? Try and come up with an equation and an expression to be minimized or maximized. It's this easy every time. Probably the hardest part is coming up with the picture. Okay? But then after we get done with that, the rest is easy. So I'm going to solve this for y, right? What do I get when I solve this for y? Y equals 1.5 million over 2x, right? Yes? And I'm going to put that into my function, which is now 3 times 1.5 over 2x plus 4x. And that's what I'm going to minimize. Right? So once I solve for y, I take that y value and put that into here, right? And that creates a function of one variable. That's all we know how to deal with right now. Calc 3, 2 or more variables. Nice. Of course, we could come up with a single expression for this. I don't think it's that important, really. But help me here. Help me clean up this function a little bit at least. 3 times 1.5 was what? 4.5? So 2.25 times x to the minus 1 plus 4x. right? Is that right? 3 times 1.5 is 4.5. Half of 4.5 is 2.25, right? This okay with everyone? At this point, I can go to Desmos like I did before. I don't think many of these problems are that difficult. But let's go for our derivative. What do we get for our derivative? F prime of x is equal to negative 2.25 over x squared plus 4. So 4x squared minus 2.25 all over x squared. There's my derivative. Of course, now because I'm trying to find a critical, I want a single fraction. So do it earlier or do it later, it doesn't matter to me, okay? But when I go to find my critical, I want it to be easy to find a critical. Downstairs, I have a critical of 0, but it doesn't make sense to have a fence, part of the fence of a length 0, right? So it's not in the practical domain. So to get my critical, all I have to do is use my numerator. F prime of x equals 0 implies what? 4x squared minus 2.25 equals 0. So 4x squared equals 2.25. So 4x squared is 9/4, or x squared is 9/16. That okay? Of course, we're going to square root, so x equals plus or minus 3/4. But of course, the negative 3/4 doesn't make sense again for the length of a fence, right? X is some number of feet, right? Yes, question? Yeah. Where are you? Yeah, but don't let me lose you. I don't want to run you over. So we have to be thinking about practical domain the whole time, right? If x is some length of feet, it's not going to be 0, it's not going to be negative. Are we okay? So we got a critical value of 3/4, right? And our second derivative, and I'm going to use this version to get my second derivative, is what, 4.5 over x squared plus 0. So obviously this is positive always. So we definitely have some kind of minimum, right? Second derivative is positive, so we know we have some kind of minimum here. Right, let's answer the question. So we had 2xy is 1.5 million feet squared, right? And we found that x is what, 3/4 of a million? Yeah? What does y have to be? A million. Yes, you with me? So we're answering the question, right? I got my x value. I have to find my y value, right? I know the area. What else do I want to know here? I got the x. I got the y. What else do I need to know? That's that minimized perimeter, right? And at the end, I want to put my units back in, right? How we doing? We okay? Is anybody okay? Yes, thank you. Candace? So any of those area problems, volume problems, uh, you know, try a few of them for sure. Go look at all my old tests and quizzes from chapter 4. I think I have a pretty good chapter 4 review in the folder there as well. Let's do a min distance problem. We ready? Or questions or anything? Anyone alive? Okay, before and Miss Girl, I'm waiting for you, so you tell me when, okay? Take your time. Okay, nice. So, before I do my min distance problem, I better talk about the distance formula. You will need this on your formula sheet. And of course, it comes from Pythagorean theorem. So we're talking about one particular segment from one point, x1, comma, y1, to a second point of x2, comma, y2. You kind of should see the Pythagorean theorem there. You should see that I need that height squared and the base squared to get the hypotenuse squared, right? To get the distance squared, right? So this one is y2 minus y1. This one is x2 minus x1. So I know my distance is going to be the square root of delta y squared plus delta x squared, right? Just the Pythagorean theorem, right? So because I put one of these min distance problems on every test, let's make sure we have this on our formula sheet, right? So here's our min distance problem. And we're going to do the same thing, the same process. Draw a picture, come up with an expression, come up with a function in two variables. That's going to be our distance formula here. Find the first derivative, find a critical value, verify that the critical value in the second derivative will be positive, right? Answer the question, meaning you'll see. So let's find the min distance from y equals square root of x to the point 2, 0. So I'm trying to find that min distance from that point to the curve. And I don't know if you realize it, but the shortest distance between 2 points is a straight line, so I'm going to always hit at a perpendicular, right? And here comes the trickiest part. What is that point? What point is that right there at the end of that segment? What's the x value? What's the y value? Well, it's xy, right? At some point xy. I don't know that point. I'm trying to find that point to minimize my distance. But what can I write in for y instead of using the letter y? Do I know anything about y? Square root of x, exactly. So there is my equation going into my expression. So I have the equation y equals square root of x. That's an equation. But I have a point that's an expression that is going to go into my distance formula, right? So, but now I can write the distance formula as a function of x, right? What's my delta y? Square root of x minus 0 quantity squared. My delta x is x minus 2 quantity squared. Make sure you're with me there. Yeah, everybody okay? Yeah? Matthew? Yeah? You're not writing any of this? You working on English paper? What paper? You shopping for no? So let's simplify this, right? Square root of, oh, that just becomes an x, right? X square root of x minus 0 all squared is just x. The other piece is x squared minus 4x plus 4, I believe, yes. And so I can simplify this thing as, oops, yeah, x squared minus 3x plus 4. So there's our, finally, our, remember, right? Take your equation, sub into your expression, create a function in one variable. So here's finally my function in one variable. Now, what's interesting is to look at this graph on Desmos. If I just look at the parabola without the radical, just look at the interior function, oh my God, so slow. Y equals x squared minus 3x plus 4. Notice that it doesn't equal 0, right? And so, and you can clearly see where the critical number is, where the minimum is. But if I write it as y equals the square root of that, I still see the same x value for my critical. Do you see it? That low point of both of those pieces is occurring at the same x value. And what I really am trying to emphasize here, that there's no way that distance can be 0. Do you agree? There's no way that distance can be 0, and there's no way for that distance to be what? Can't be 0. I think I see a minimum, but it can't be maxed. There's no way to max that distance. It's going to go to infinity, right? Okay, what's next? Derivative, yeah. So our derivative, d prime of x, is the derivative of the inside over 2 times the square root of x squared minus 3x plus 4. And the derivative of the inside is what, 2x minus 3? Nice. Do you notice that the downstairs is 2 times my original function, and that's how I will prefer to write it on most of these problems. I get 2x minus 3 over 2 times d of x. Why? I don't care about the denominator being 0 because I know it can't, right? I don't need a critical from the downstairs. That distance can't be 0. So all I need is a critical from the upstairs, right? So d prime of x equals 0 implies 2x minus 3 equals 0, which means x is 3/2. So I have my x value now, right? I want to verify with the second derivative that that x value gives me a positive, right? I want to find the y value. I want to find the distance. Yes, you with me? Good, let's start with our second derivative. So d double prime of x, and I'm going to use the quotient rule. I'm going to use a quotient loop. Upstairs being 2x minus 3, down derivative being 2, downstairs being 2 times the distance, and the derivative being 2 times the distance prime, right? I'm trying to keep this one abstract because it gets really, really messy if I use the actual algebra, right? So I know I need the downstairs squared, so it's going to be 4 times d squared of x. Is that okay with everybody? So for my quotient rule here, it looks like I get 4 times d of x minus 2 times 2x minus 3 times d prime of x all over 4d squared of x. It's a little weird when you're doing this the first time by keeping it all so abstract by this, but in a second you'll see why it will really pay off. And I invite you to do it non-abstractly. I invite you to do it with the actual functions, but you'll see it's hell. Well, what's funny about this? What happens when I plug in 3/2 here? When I plug in x's 3/2 here, what happens? Yeah, and what happens when I plug in 3/2 to d prime? It's the critical value, right? So 0. So it's kind of nice. I don't have to really think much at all. D double prime of 3/2 is 4 times d of 3/2 minus 0 over 4 times d squared of 3/2. So that's just 1 over d of 3/2. Well, the distance is definitely positive, right? So since that d double prime is a positive number, I know for sure that critical value is going to give me a minimum. How are we doing here? Nice. We still have to answer the question, right? We found our critical. We know it gives us a minimum. We still have to find the point and we have to find the distance, right? Find the point xy, or x square root of x. So all we have to do, so we know x is 3/2, y is square root of 3/2. I'm just so used to rationalizing those things. It's just I can't stop myself from doing it still. So there's our point. We know the x-coordinate is 3/2. The y-coordinate is square root of 6 all over 2. We need to find the distance. Right? So d of 3/2 is square root of 3/2 squared minus 3 times 3/2 plus 4. Right? Plugging into my distance formula to find the minimized distance. So square root of 7 over 2 is the distance. I guess some conclusion would be good. Well, I don't feel like writing it, but we know the point we found, it gets us the minimum distance to the point 2, 0, right? On this line y equals, on the curve y equals square root of x. How we doing? Yes, Nathaniel? Yeah, so remember, I was trying to find a point that will, on the curve y equals square root of x, that would give me the minimum distance to the point 2, 0, right? Look at that picture again. I'll come back to this in a second. Right, I'm on the xy axis. I've got the curve y equals square root of x. I found from 2, 0, I found the point, what, 3/2? Yeah. So I found the point 3/2. Oops. What did I do? Oh yeah, there it is. I found the point 3/2 square root of 6 over 2. Right? And so that gave me the minimum distance here. I guess I'll write the conclusion. How about that? A min distance of square root of 7 over 2 was found from the point 2, 0 to 3/2 comma rad 6 over 2 on the curve y equals square root of x. Something like that. Doesn't have to be exact. Just some kind of summary of the whole thing. Let's see who's got the big brain on. My green segment and my green line are what to each other? Perpendicular, right? Perpendicular. When I minimize my distance, I'm always going to hit at a 90-degree angle, right? So lines that are perpendicular are have what kind of slopes? Perpendicular lines have what kind of slopes? Yes, opposite of each other and reciprocal. So the slopes of those two lines or segments should be opposite reciprocals. What's the slope of my my green green dash red line. What's the slope of that one? I'll call this line T for tangent and this line S for segment, okay? So what's the slope of my tangent line? Well, I just have to get the tangent, right? I have to get the derivative and plug in what? 3/2, right? So 1 over 2 square roots of 3/2. Square root of 6 over 6. What is the slope of my segment? So the blue and green dash, what's the slope of my segment? Killing me today. Square root of 6 over 2 minus 0 over 3/2 minus 0, right? Oh, 3/2 minus 2, sorry, right? Yes, you agree? Just y2 minus y1 over x2 minus x1, right? So what is that? Square root of 6 over 2 over 3/2 minus 4 over 2. Which is, help me, square root of 6 over 2 divided by 1/2. Wait, did I lose something? Should have a negative somewhere. This one should be negative, right? Oh, minus 1/2, right? Minus square root of 6. Okay, I like the positive negative. Yes? Do I did something wrong? Help me. Let me just double check this one. Oh, this one I did wrong. This should be square root of 2 over 2 square roots of 3. I rationalize with square root of 3. Oh, no, that's right. Yeah. No, square root of 6 over 6. Oh, but let's look at the reciprocal of that. Sorry. That might help. So reciprocal of that is square root of 6 over 6. And if I rationalize now, there it is, I get rad 6. So the reciprocal opposite, right? Reciprocals. Look at all of my distance problems on old tests and quizzes in Chapter 4. Look at the test review in Chapter 4. Right, you got 4 homework problems due for me Monday. Yes? Anybody need to see that list again? It's on Blackboard, right? Should be in your email. Do some problems. Geometry, min distance problems. I always put a min distance problem on. All right, have a great weekend.